Today we're extremely pleased to have Feras Saad to come and visit us from MIT, from the Computer Science and Artificial Intelligence CICS lab, to speak about a topic that I think is extremely important and upcoming, to a point that it really got my attention after I read an article review from Zubin Garamani on the New York Times about 4 months ago about the work at MIT. So we're extremely pleased to hear about probabilistic programming and automatic data modeling. And there is,
thank you.
And we're ready to go.
Sure. Thank you. Excellent, thank you. All right, good afternoon, everyone. Thank you very much for showing up. And thank you to Professor Zabaris for the warm invitation and the nice introduction. Today I'll be talking about probabilistic programming and automatic data modeling. So let's start by considering the following plot. There's some variable which seems to be evolving as the time increases. Now, the moment we look at this plot, our mind starts building some kind of a model for what's happening, and we start recognizing particular patterns in the data. For example, the first thing we notice is that, on average, the value of the variable is increasing over time, linearly. And there's a large peak whose amplitude is growing as well, shown in the red boxes. There are smaller peaks after the large peak, and there are periodically recurring smaller peaks prior to the large peak. In addition, as a consequence of having some kind of model in our mind and detecting these patterns, we can imagine forecasting the data in the future. I mean, you could just do with your hands how you imagine the time series will evolve, and we predict it will look something like this. And in fact, what you're seeing over here is global airline passenger volume from the year 1948 to the year 1962. And the different seasonal peaks correspond to travel in the summer, in the spring, and in the fall, around New Year's, around Christmas time. So what we just did there is a small experiment of what a data scientist or a statistician does. Now, what we did heuristically on the board is actually very, very hard to do rigorously for a lot of reasons. So Drew Conway, who's a data scientist, came up with this sort of Venn diagram, which I think summarizes very nicely some of the challenges of data science these days. The first thing is that everyone who's of high qualifications is in the center, number one, but these people are overloaded and very rare and very hard to find. Now, in academia, we're sort of over here where we have substantive expertise and knowledge of statistics, but we don't actually have the real problems that people in the real world are actually trying to solve. So we publish papers, but translating those papers to the real world is a challenge. And for every single sort of part in this diagram, we can identify some of the key challenges with statistics or practicing data science. Andrew Gelman has this very nice quote: "Statistics is hard like baseball or knitting. We have to accept statistical incompetence not as an aberration, but as the norm." Okay, so in today's world, let's say you have some time series like the one we just saw, and you want to ask what patterns exist in the data, like we saw the peaks and the trends, and we're also interested in predicting values of the variable in the future. What we do today is we go to a data scientist or a statistician, and we ask them to solve this problem for us. But doing this, of course, requires manual labor, it's very time-consuming, it's costly, and it needs lots and lots of expertise. In this talk, we're going to talk about ways in which we can remove the middle person, so to speak, and instead go from data to probabilistic programs which represent likely ways that the data was generated. What we're going to first do is talk about a general way to do this, and we're going to apply the approach to two specific domains. First, we're going to talk about how to discover models automatically for time series data, which will be the first part of the talk. And the second part of the talk will be how to discover models for multivariate data tables. And throughout, we're going to show how the probabilistic programs that we learn can be used to both find structure and make predictions for future data. There's a collection of theory which I'm not going to talk about today, but the slides are online and people can refer to the associated publications for those who are interested in those aspects. So like I said, in the first part of the talk, we're going to talk about models for time series data and go over the way that we implement that system. In the second part, we're going to talk about discovering models for multivariate data tables. So let's start with a very high-level overview of our system and how it works. The first thing we're going to do is we're going to specify a domain-specific language, which is a space of probabilistic programs for time series. So these are programs these are basically simulators for time series. And we're going to define a space of such simulators. We're going to endow this space, the space of programs, with a prior distribution. And for any specific simulator, we know, because it's a probabilistic simulator, what is the probability of the values on the y-axis given the time points on the x-axis. So for everyone here who knows Bayesian reasoning, and I'm encouraged in my talks with people today that it's actually very common in CICS, we have all the components for a posterior distribution over programs. And so what we're going to do is we're going to combine the data with our space of programs, our space of simulators, and the likelihood and the prior to derive a posterior distribution over likely programs that generated the data. Once we have these programs, they're going to be designed in such a way that their surface syntax reflects the key patterns in the data. So we're actually especially interested in interpretable programs, not black box programs that are hard to understand. And second, because the programs or the simulators which we're generating are probabilistic, we can use probabilistic inference and then try and find what are likely values of the time series in the future. So now we're going to look in a little bit more detail about what is this domain-specific language for describing time series. In order for all this to work, we need a very good family of models over which we're going to try and search over. And so the Gaussian process, which people here might be familiar with, is a very rich family for modeling time series with a lot of different patterns. Here's how it works. A GP is a random function, which I'm denoting f, which maps a list of x's to a list of y's. And what's unique about it is that it's random. So in a standard function, we have a list of time points x1 through xn, and it spits out a bunch of values of the time series. And what I'm plotting here is the value of that function. A stochastic function, on the other hand, is random. So every time I invoke it, I get a different set of outputs. And so what I'm showing here are different draws from the Gaussian process. All right, each curve is a realization of the Gaussian process. Now, statisticians have been using Gaussian processes for decades. And what's really neat about Gaussian processes is that they are parameterized by what's known as a covariance that dictates the shape of the time series. And so what researchers have been doing recently are saying that we can take primitive temporal patterns that parameterize the Gaussian process, things like periodicity, linearity, smoothness, etc. We can compose these patterns using sums and products. And as a result, what we can do is obtain, using the Gaussian process, all sorts of interesting temporal structure. Things like local variation, linear functions, multiscale variation, periodicity with noise, and so on and so forth. So once we have a Gaussian process model for a specific time series, we can discover the patterns by looking at the covariance k, which is going to decompose according to the primitives and sums and products of those. And we're going to be able to make predictions for new data. Okay, a little bit more technically. Formally, the Gaussian process says for any list of inputs, time points x1 through xn, the outputs are jointly distributed as a multivariate normal, whose covariance matrix is defined by a function k, a positive function k. And we just use this notation to indicate that f is drawn from a Gaussian process, the random function with a specific covariance. So what is this covariance? Well, here's just a picture of how it works. Let's say I fix 2 time points, x and x prime. And each time I draw a random function, I have realizations. The red ones, the blue ones, the orange ones, the green ones. And k of x and x prime is telling me what are the covariants of f and x prime as I repeatedly sample over and over again. And crucially, k is going to dictate what are the patterns in the underlying data. Okay, now one way that we can represent Gaussian processes, remember it's just a multivariate normal, not extremely complicated, is to just say, all right, I have a simulator which says, give me time points, do a bunch of math, and spit out time series. But obviously, these programs in the middle are very, very hard to understand, right? Like probabilistic code, if I hand it to you, you guys have no idea how the plots in this part of the slide correspond to programs. So we're going to do away with probabilistic code and instead define a domain-specific language, which is a high-level representation of the data generating process. So for example, in the first row, we're saying we have a time series which is smooth with some parameter. And the realizations of this random process are just smooth curves. On the second row, we're saying we have a random process which is a product of a linear trend and some periodic structure. And so now we can go here and pretty easily now understand why we're seeing realizations which are periodic and linear. Similarly, on the last row, we're saying there's a change point between two different time series. In the first component, there's linearity, which is what we're seeing here. And then at time 0.5, we're switching from linearity to periodic structure. So once we define a high-level domain-specific language, it's actually much easier for us to interpret the models as compared to arbitrary, simulation code. So this is like a key character in our process. Now, being computer scientists, what we do is we define a language using a grammar. Hopefully some of you have seen grammars before. And basically what the grammar tells you, the way you do it is you sort of say, a covariance function, k, which is what we talked about earlier, which parameterizes the shape of the time series, is either white noise, constant, linear, smooth, or periodic, and these are the numeric parameters v, and these are what are called the primitives. And then there are compositions, which are sums of two kernels, products of two kernels, or a change point at some point between some kernel and another kernel. And so this is now our language for time series. Okay, now that we specified a context-free grammar, it's very easy to make it a probabilistic context-free grammar. The way we do it is we just specify, all right, what is the probabilities of starting with of generating any specific program? So these are defined recursively, of course. So our sort of numeric parameters are distributed as a gamma distribution. And then we have for the primitives just different probabilities, say they're equally weighted. And then by the chain rule, we have to multiply with the probabilities of the number of the numeric parameters. And then for the sums and products, it happens similarly. And so if I give you any specific program in the DSL, you can very easily use these rules to find what is the prior probability of having generated that program, just by factoring it according to the simple rules of probability. Okay, so now we've gotten this far. I'm going to make a small case for why Bayesian sampling over programs is important. Remember, we're emphasizing that what we're generating are a collection of probabilistic programs that are likely to have generated the data. In machine learning, someone might say, or even in programming languages, look, why are you doing all of this stuff with priors, etc.? Why don't you just find the program that maximizes the probability of the data? You have a space of programs, find the maximum likelihood estimate. Now, hopefully most of you here don't need too much convincing that Bayesian reasoning is sensible. But let's try and sort of visually understand why it's sensible in this, why it's especially sensible in this case. Recall that for some observed data set x1, xi through yi, I can find the covariance k, which is the argmax over all possible programs of the likelihood, which is the multivariate normal of the y values with the specific covariance. Now, leaving alone how we do that maximization, suppose we could. Why is k-opt not the best solution? Okay, so suppose I show you these particular dots. One particular program that can model these points is given by this monstrous, expression, which is basically saying just interpolate the points. Because our program space is so rich, we can actually perfectly fit any specific time series and just take the noise to be lower and lower and get the likelihood to be higher and higher. But if I tell you a program, or if I tell you the model for this time series is just connecting the dots, a kindergarten student could do that, right? You don't need any sort of sophisticated technology, but you can't use this. You can't use this for prediction, definitely not, nor can you use it for interpretation. So we can fit models with arbitrarily high likelihood, but which are useless. In contrast, another program in our little Gaussian process language is to say there's some periodic structure with a bit of noise. And this is actually a very useful program. It explains the pattern in the data, and it will allow us to forecast into the future, even though it fits the data less than the interpolation model. It assigns a lower likelihood. So we have simple programs which could be useful versus very complex programs which are useless. And the likelihood doesn't really tell us how to choose between these. And so having a prior is a way of preventing overfitting. And so hopefully most of you understand or know already that sort of according to the Bayes rule, the posterior probability of a program is the prior times the likelihood. And this is a very sort of principled probabilistic way to regularize. Other things you could do are like program length, et cetera, or penalize it in some way, or complexity score, but those aren't really easy to reason about systematically, whereby specifying priors is and allows us to encode more knowledge into the types of time series we want to see. Okay, but now we set the posterior. Why not find the single program who has the largest posterior probability? Right. So we said we don't want the maximum likelihood, but what if we want the maximum posterior probability program? And in Bayesian, this is known as maximum posteriority. And here's hopefully a diagram which can make the case. So suppose I have some set of data shown over here, and two candidate hypotheses in our space of Gaussian processes are there's some line with noise through it, or there's periodic variation with noise. These are two rather sensible hypotheses for the data. Now, suppose our held at data shown in red has this particular pattern. Well, what we'll see then is that here, our linear model actually fits or predicts the held at data reasonably well, whereby the periodic model just completely overfits. It's found a structure which is spurious, which isn't really there. But of course, we could easily imagine a second scenario where the held at data actually looks like this. Well, in this case, our predictions from the linear model, okay, they're not that bad, but they do underfit, which is what we're seeing over here. There's some points which are well out the regime. But the predictions from our periodic model are actually very accurate. And so by sampling programs and not finding the single most likely program, what we can do is sort of aggregate, do model averaging, model aggregation, or sample models according to how much evidence there is for them being representative of the data generating process. And of course, because we're in these very rich space of structures, posteriors are definitely not unimodal. There's many, many different structures which can represent a data set. Yeah. Okay. So now you're coming to tell me, look, I'm a user of the system. What should I do to use your system? And what I'm going to show you now is an implementation of the approach in a probabilistic programming language called Venture. So going back to our favorite time series, the first step is we load the time series data, and this is code in a probabilistic programming language called VentureScript, which sort of shares some syntactic similarities to JavaScript. So we load up some observed data and some test data, and then here we're sort of doing a resampling step where, remember, we're doing Monte Carlo estimation, and a lot of this is embarrassingly parallel. So we're going to say, run 100 Monte Carlo chains in parallel. And what we're going to do is first we're going to sample from the prior a DSL program, which is returned by this stochastic function. And I'll show you that in the future, and in the coming slides. Then what we do is we compile that program to get a Gaussian process model, which is an actual representation of a statistical model. This is just DSL code that looks like this, domain-specific language code. And then we're going to say, look, let's observe the model at the specific x's to be equal to the y's. And then what we're going to do is we're going to start synthesizing new programs, and that's using these Monte Carlo moves on both the structure of the program, which is like what is the sums, the products, how many kernels there are, and also on the hyperparameters, which are the numeric constants. And then the final step is to obtain forecasts by saying sample from all the 100 posterior samples. Here I'm showing 1, 2, 3, 4, but in reality here we'll have 100 predictions from each of the Gaussian process and aggregate them for me. And what we're showing here are sort of the average predictions from all of the programs that we've synthesized. Okay, so the first thing we check as machine learning people is, are our results any good? So let's look at it for forecasting. What we did basically is say, all right, this is a method which you just throw in data, you get predictions. How does it compare to other methods? Things like Gaussian processes, where you're using a fixed covariance structure, not trying to learn one, or ARIMA processes, where you're learning the order of the process. Facebook Profit, which is an algorithm that Facebook have been promoting recently for learning from time series. A non-parametric model, hierarchical Dirichlet processes with hidden Markov models, and just a basic linear regression. And what we find is that most of these sort of have somewhat erratic behavior. I guess ARIMA is maybe the most competitive baseline in this case. Even linear regression does more sensibly than I guess Facebook Profit, which is telling you a lot about Facebook. So yeah, I mean, you can sort of try and benchmark the quality of the results across data sets with varying different patterns. And what we find is that this system is in fact able to forecast on a short-term horizon much more accurately than existing models for time series where the user provides no input. Obviously, if the user provides input, you might be able to do much, much better. But sort of as a baseline technique for all these various data sets, roughly this approach is sort of delivering accurate results. The second thing that we look at is, all right, can we detect patterns in the data? Now remember that the results of our procedure is a bunch of programs. Now, no one's going to sit down and read the source code of the programs, but what you can do is that you can do very simple syntactic analyses, because we've defined our programs to be simple and interpretable, so we can extract key properties from the surface syntax. And for a variety of data sets, what we can do is we can start asking, what are the different posterior probabilities of having that particular structure in the data? So here, for example, it's clear that there's white noise, because almost all real-world phenomena have white noise. There's no change point, because the data is sort of periodically evolving. And there's very low probability of linearity, but there's periodicity. And we can see for all these different, for example, in the call center, there's a very high probability of a change point. Because initially it was increasing linearly, and then there was a significant drop, and there's a linear increase with a different trend. And so what the system does is, by sort of sampling these programs from posteriors and trying to summarize the structure, is to allow the user to sort of obtain estimates of what are the probabilities that different structures exist in the time series. Are there any questions at this point? I'm happy to slow down if there's clarifications. But otherwise, I'm also happy to go on. Okay, good. So a key sort of feature of our approach is that we're implementing probabilistic program synthesis using probabilistic programming technologies. And so what that makes it easy for us to do is rapidly prototype and implement complex learning algorithms using new programming languages which are especially designed for statistical inference. So for example, here I promised you that we're generating DSL code from some prior. Well, what is that prior? It's basically our context-free grammar expressed as a probabilistic program. So each component corresponds to some generative code. So here gamma is sort of like a log logistic transform, so that's how we sample these numerical parameters. Sampling the kernels, the base kernels, is sort of done with this chunk of code. And sampling the composite kernels is done with this chunk of code. So here what the user is saying is they are encoding the probabilistic context-free grammar using a probabilistic program. And then this is sort of the main harness which generates a program according to these probabilities. And we'll get into, you might be wondering, what does this structure mean? What does this hypers mean? What does this tilde mean? These are all sort of ways in which we're going to be giving the generic inference algorithm hints as to how to do inference and try and learn for any specific time series, to try and learn which execution was actually undertaken by the model. I won't go too much into this, but the second step is to basically take the DSL program, which is just a string generated according to these probabilities, and to compile it into an object in memory that we can then execute inference against. And this compiler is 20 lines of code. It's actually an interpreter. It's like 20 lines of code which takes a string like this and dumps out an object which now we can use as our target for inference. And then the third step is like actually sampling from the posteriors. So how do we do it? I'll show you a very simple example, but it should be easy to extrapolate to more complex examples. So let's suppose we have a particular DSL program for a time series, which is given by a product of periodicity and linear patterns. So this particular inference move, called Metropolis Hastings on structure, is going to randomly select a node in the tree, which is going to select that particular node, and then propose from the prior a subtree, and compute sort of the right ratios to determine whether to accept or reject that move, according to a Metropolis Hastings MCMC move. And these, of course, the user only specifies infer Metropolis Hastings. The user isn't writing any code to compute the likelihoods, compute the ratios, etc. So one of sort of the advantages of using these new probabilistic programming systems is we can do very complex operations on the computation graph as concise programs which are saying, go do some inference on the structure of the program. Another thing we can do is hyperparameter inference. So let's say I'm happy with my structure, but I want to tune the hyperparameters. The way we do that is say, go do some inference on hyperparameters. And those correspond to the numeric constants in the computation tree. And the way we do it, again, is by proposing new values and determining whether we should accept or reject those new values. Again, in an automated way, according to the sort of MH tool. Now, of course, for people who use TensorFlow, you might say, this looks very much like a computation graph. Why are you doing MH on numbers? Why don't you use gradients? And so we can. The way we do that is by expanding out these nodes into the actual sums and products and exponential functions and divisions, etc., that they're comprised of. And the system implements reverse mode auto-differentiation. So it can automatically differentiate the likelihood all the way down through to the numbers, which are these things over here. And if you want to do that by hand, it's a very complex algorithm. But sort of having generic inference machinery allows you to abstract very, very complex algorithms using concise features. Okay, so what we just talked about are ways you can use Metropolis Hastings for tuning hyperparameters or gradient inference. You might say, like, why would I use one or the other? And this plot, I think, is a nice example of some of the trade-offs of using, MCMC sampling versus gradient-based optimization. So our time series is a periodic function, and the black dots represent the observed data. In the top, what we're doing is we're trying to fit a Gaussian process. We're trying to fit a Gaussian process with a periodic kernel using Metropolis Hastings to infer the hyperparameters. And in the bottom one, we're using gradient optimization to infer the hyperparameters. And so predictably, they look pretty similar. There's not enormous difference. But if we look at the posterior landscape, so the periodic kernel, the hypers correspond to a length scale and a periodicity. Now, periodicity of sine functions is multimodal. So this has a period of 3, but it could also have a period of 6. It could also have a period of 9. It could also have a period of et cetera, et cetera, et cetera. They're not all equally likely, because under the prior, maybe we're sort of regularizing toward smaller periods, the most concise period. But there are modes sort of representing the integer multiples of the period. If you use something like optimization, you might find the local minima and just get stuck there. Whereby if you use something like Metropolis Hastings samples, which is what I'm showing you in the blue over here, you could get sort of samples from different modes relative to their weights. Now, in gradients, what people do is like restart the gradients multiple times and somehow take the best average, the best fit, etc. But there's really no principled way to use like results of gradients. On the other hand, gradients are much faster. So there's always like trade-offs between computation time, how much posterior uncertainty you want, model fit, and so on. So this here is sort of showing how different algorithms explore the posterior landscape differently. Okay. Another sort of feature of using probabilistic programming to synthesize programs is you can vastly simplify the complexity of implementing complicated inference problems. So what I'm showing here is a comparison of the system that we built in Venture to a similar system, which is built in previous research by using MATLAB and Python libraries. So like our main system, which I basically showed you in the slide deck, is sort of around 100 lines of code, whereby using sort of custom or hand-coded implementations can reach to thousands of lines. And sort of the Gaussian process libraries, which are reusable, the user never has to develop them. It's the developer of the language who develops them. And we benefit from using generic inference implementations, which are, these things: infer metropolis hastings, infer gradient. These are all part of generic inference implementations, which we can use over and over and over again for different models and for different settings. Okay, so maybe I'll spend a little bit of time about sort of some theoretical considerations of doing this. Can I just go do this? So for those of you who are familiar with hierarchical Bayesian modeling, you might see sort of in statistics these kind of graphs, right? Where you have some probabilistic model family, you have a model structure, you have model parameters, and you have data. And the inference problem is going from data all the way up to a particular model structure. So the forward model is sort of the generative, the forward model is going downwards, the reverse model is going from data and inferring likely model structures. And in probabilistic programming terms, what we've done is sort of translate maybe this heuristic description into model families become domain-specific languages, and I've showed you an example using the Gaussian process. Model structures become actual DSL programs, and then model parameters become the numbers in those programs, and the data is just the data. But there actually has to be some care to be, implementing this does require some care. There's sort of standard results in theoretical computer science which says, if you just specify arbitrary simulation code, that doesn't guarantee that the Bayesian inference problem is well defined. You may specify forward models for which it's actually impossible computationally to go from data to posteriors over unknown structure. So things we have to care about are whether the prior is well defined, whether the likelihood of data given the program is finite, does the posterior distribution even exist, do inference algorithms converge, et cetera, et cetera, et cetera. So if we want to be sort of principled about this approach, these are some considerations that we have to consider. And there are some reasonably sensible conditions that we've shown are sufficient. They're not necessary, but they're sufficient for this thing to be well defined. Things like showing the prior is normalized, the likelihood is normalized, and the likelihood is bounded. And then if your setup sort of satisfies these constraints, then you're guaranteed to have a posterior distribution that exists. But checking that the prior is normalized might be easy if you're using a univariate distribution or something. But here, actually, what we have is a sum over an infinite set. And this is a sum over all possible programs in our language. Now, obviously, that's countable because programs are strings, so strings are countable. But it actually turns out that solving this problem is equivalent to the halting problem. You need to show that the simulator for your language halts with probability 1. And that's a hard problem in general. So that can be very subtle as well. So in the left, what I'm showing is an example of a program which is normalized. And what this program does is with probability 0.49 recurses, and with probability 0.51 terminates. On the right, I'm showing a program with probability 0.51 recurses, and with probability 0.49 terminates. And so you can actually show that the program on the left halts with probability 1, and the program on the right diverges. So if I run the program on the right many, many times, with non-zero probability, I'm going to have an execution which runs forever. And that's not only like some esoteric problem, that's actually really important for engineering. Because if you want to engineer these systems, you can think of as some kind of like fundamental instability about the way you've encoded the prior sampler. And so, we need to be careful about these issues. So what this rules out is that, for an arbitrary domain-specific language, we can't just go and write, priors and hope that they make any sense. But if our domain-specific language, like in the Gaussian process case, was generated by a PCFG, there's actually ways, according to some very classic and interesting research, to check whether that program halts. And it's not hard. I can show you in like 2 slides how to do it. So remember, this is our prior distribution over programs for Gaussian process time series. What we do is we express it in Chomsky normal form, and we label the transition probabilities across the top. And then the second step is to build the expectation matrix of that PCFG, which is just a simple transform from the CNF expression to a matrix expression, and you find the eigenvalues of that matrix. And the spectral radius is the absolute value or the modulus of the largest eigenvalue. And if that's between -1 and 1, it halts. So I think this is a pretty neat insight because it actually gives us a way to mechanically check whether a user is writing programs which are guaranteed to halt. So you can take the user's program and you can take a simple analysis like this and tell the user that you've written a program which is actually going to be very problematic versus you wrote a program which is actually going to be, our system's actually going to be able to handle. And for those of you who are interested, there's all sorts of interesting related literature from programming languages, from probabilistic machine learning. That's sort of, this research is, combining a lot of those different ideas and trying to sort of synthesize probabilistic programs for data in a Bayesian way. Okay, so that was the first part of the talk. How do we discover models for time series data? I just flew through a system, but hopefully you guys have some intuition for how it works. In the second part of the talk, we're going to talk about how to discover models or synthesize programs for multivariate data tables. And so this was our old picture. We're going to change that picture where instead of time series, we're going to have database tables. And now our prior is going to be over programs that generate database tables. And we want to generate probabilistic programs which are sort of specifying how to generate rows in the table, sort of a simulator for the rows. That's what we want to learn. And once we have these programs, we can do all sorts of interesting things. We can say, what are the probable predictive relations in the table? What are the probable values for missing fields, et cetera, et cetera. But this is very hard. Okay, so how many people here have used Scikit-Learn before in any context? A few people. Okay, so Scikit-Learn is a machine learning library in Python, which is, for many purposes, like the state-of-the-art machine learning library. And what they tell you to do is, if you want to answer a statistics question or a machine learning question, you have to start at their little dot here, and then sort of navigate through all these different sort of decision points until you find the algorithm that works for you. So navigating this is obviously very, very complicated. So for example, if you have less than 50 samples, Scikit-Learn can't help you. Already you have to get more data. Nothing less than 50 samples. All right, if you have more than 50 samples, it's ultimately going to lead you to either a clustering algorithm, a dimensionality reduction algorithm, classification algorithm. And in many cases, you're going to end up with tough luck, which happens like if you're trying to predict structure. So standard machine learning solutions, which people in the field have been developing for the last 10 years, 20 years, 30 years, don't actually have much ability of predicting any kind of structure. They're very good for parameter estimation and sort of doing all these specific kind of tasks, but if you actually want to learn causal structure or emulate causal structure, you're mostly out of luck. Okay, so then why? Why is it the case that predicting structure leads you to tough luck? It's because structure learning is very hard. People who are familiar with classical Bayes nets know that estimating a Bayes net from data like this, it's slow, can be unreliable. It's hard to obtain uncertainty over models and hard to combine this with like continuous and discrete variables. It's hard to combine with accurate quantitative models. It's hard for users to ask questions. So historically, Bayes-net structural learning has been a very, very hard thing for statisticians to do. Now, in a series of papers, what we were trying to do is to make structural learning easier. The problem we're trying to solve, I guess, is, this orange link over here, which tells the user that they have tough luck. We want to get rid of that orange link. We don't want users who are trying to predict structure and don't know much about the data to have tough luck. So the family of models we're looking at are based on Bayes nets, and we're trying to develop new solutions that address some of the classical features. So we all know today, for example, with cloud computing and parallel computation, we can scale inference to hundreds of nodes or even thousands of nodes. Uncertainty over model structure can be addressed by using Bayesian Monte Carlo rather than heuristic search and score techniques from the Bayes-net structural learning field. We can sort of make it possible for people to use accurate models by expressing these Bayes nets as probabilistic programs, which are sort of simulators and which are functions that take inputs and outputs. And so this allows people to combine automatically discovered Bayes nets with custom Bayes nets or custom distributions. And sort of for mixed data types like continuous variables or discrete variables, we're going to try and design a domain-specific language which actually accounts for those types of distributions. Okay, so then just like we needed a Gaussian process for time series, we need an analogous model family for data tables in order for any of this to work. And that's sort of the first component of any kind of synthesis system, is what is the language that specifies the probability models. And so one way to do that is by using nonparametric Bayesian modeling. Okay, you don't need to know what that means. I can hopefully in some slide give you an intuition for what that means. So suppose we have a data set of observed variables A, B, C, D, and E. So there's 5 variables. And they are characterized by a complex latent variable model where the shaded nodes indicate that variables are not observed and lines indicate dependencies. And there's sort of a weak dependence. So A, B, and C are sort of categorized by this part of the Bayes net, and D and E are categorized by this part. And what I give to you are 30 observations. So I run this Bayes, I sample from this Bayes net 30 times, and say all the values are between, 0 and 20. And so the color of the cell is indicating how high the value is. So that's column A, B, C, D, and there's 30 rows. And so this is sort of just representing some data table from sampling that particular Bayes net. So one hypothesis for the data is to say, look, I'm going to do the most simple thing possible, and statisticians sometimes do this. I'm going to say all variables are independent. So for each variable A, B, C, D, and E, I'm just going to model it independently. There's no multivariate structure in the way the data was generated. That's one hypothesis for how the data is generated. Okay, a slightly more sensible hypothesis is to say all the data is related. So here I have a Bayes net. My hypothesis is that rather than have a separate model for each column, I'm going to have one model which is responsible for all the columns, and I'm going to say, why don't I use a mixture model to estimate the joint distribution? And so here what I'm showing is sort of 3 different mixture components. So this variable h1 can take values 1, 2, and 3, and then condition on h1, everything is independent. That's another hypothesis for this distribution. A third hypothesis, which is the most likely, is to say A, B, and C are probabilistically dependent. So let me go learn a model for A, B, and C. And then separately, D and E are probabilistically dependent. So let me separately learn a model for columns D and E. And with only 30 data points, it's very unlikely we're going to have enough evidence to detect a weak relation. So the hypothesis that A, B, and C are dependent is actually going to be are dependent and independent of D and E is going to be quite likely. Now you can keep playing this game. You can say A is going to be independent of B and C, and D is going to be independent of E. So you can try and partition the variables in this way. You keep going and going. But these are known as factorial mixture models. And there's a method called cross-categorization, which roughly takes a data table like this and samples from a posterior distribution over Bayes forests, Bayes nets, which are comprised of multiple independent components, and tries and learns which Bayes nets are most accurately describing the data generating process. So it's like a structured learning algorithm. And because it's non-parametric, it has to learn all sorts of things. It has to learn, like, for each mixture model, how many components are there, how many different independent mixture models are there. And so this is like some hierarchical Bayesian model, which actually man years of engineering and multiple venture-backed startups have been throwing resources towards because they're actually pretty good. So what I'm showing here are 4 different data sets from the UCI machine learning repository. So there's like a wine data set, an automobiles data set, a credit data set, and so forth. And what I'm showing in the left here on the first plot are actual data from the data set. So these are for some automobile, the compression ratio versus the aspiration. And we can notice that there's some interesting structure over here in the observed data. If I fit a linear model, a GLM, a generalized linear model, it's not going to be able to detect that there's a missing regime over here. Whereby these factorial mixture models are able to capture bimodal dependencies and more generally multimodal dependencies. Other things you can see, for example, over here, if my observed data has this interesting U shape, the best the linear model can do is a cloud. Give it as much covariance as you want. It's never going to look like this. Whereby the factorial mixture models that I showed in the previous slide are able to emulate distribution. And we see the same sort of pattern over here, where there's no data over here in the observed, and so our simulator also learned that there's no data here, but a linear model is just a cloud. And similar over here, where you have heavy tails, these factorial mixtures, because they're empirical models, not parametric models, they can sort of accurately represent heavy tails, whereby simple linear models can't represent those kind of heteroscedastic behavior. Okay, so enough with tutorials. Let's actually see how this works. And I'll not spend too much time on this. But what we're going to do is try and apply this technique for studying a database of Earth satellites. So we're going to have a database where there's 23 variables, which now this is like a flipped table. Usually columns are variables, but for the slide, the rows are the variables. So we have things like the name of the satellite, and each column here is a particular satellite orbiting Earth. The first one is at the International Space Station. So it has all of these numerical characteristics, categorical nominal characteristics, etc. So this is like a real-world database from this URL. It has arbitrary missing data points, so we need like a robust method to be able to learn this. And our goal is to build models for this particular data table. And so to do that, what we've done is we've built a system where, sort of using a web interface, users can specify data tables. So this data table over here represents, it's a Python data frame, and it represents the different satellites. Now they're rows and the columns are variables. And what we're going to try and do is first tell the system, go guess for me what the schema of this data table is. So the user says, guess the schema for the satellites table, and the systems come back and says, all these variables are nominal, all these variables are numerical, and ignore the name because you don't want to probabilistically model the name. That's just a unique identifier. So here the system is doing a little bit of guessing for what are the different data types. And then what we do is we sort of initialize eight of these structured learning algorithms and analyze them for, say, 100 seconds. And so here what I'm showing are different subsamples of the data where we've now done this partitioning of the columns and the rows of the data. So as I had showed in the previous slide, our model builder tries to find a mixture model over the rows and an independence model over the columns. And different posterior samples have different hypotheses for how the data should be partitioned. Remember, here each column is a variable and each row is a satellite, and the color of the cell indicates the magnitude of the value. And these horizontal lines indicate sort of how the mixture model was learned. Okay, so then how can you use this? Well, one thing we can do is we can say, hey database, go simulate for me. Now that you've built this model, go simulate for me sort of the country of a satellite and the purpose 1,000 times. Generate 1,000 fake satellites for me. As a consequence of building a generative model, we can now simulate from predictive distributions. And we can compare, for example, the quality, how much the simulations match the reality. So in blue is a frequency. This is a histogram of different country and operator pairs. And we can sort of get a sense that even though the fit, of course, is not going to be perfect, the relative proportions of our simulations are roughly well matched with the actual empirical data. And so here what we're doing is we're like extending SQL, which can only let you select, with simulate queries. And so you don't need any statistical expertise to be able to do something like this, right? You can just write the query. We basically went from a data table to a guess of whether the variables are numerical or categorical to sort of simulations from predictive distributions. Other things we can do are just doing some more assessment of how good our models are. Sort of here we can select the perigee of a satellite is like its orbital radius, or the nearest point in its orbital radius. We can select from the table and just do a histogram, and we see that there's roughly 3 modes. And we find, we can now simulate from our predicted distribution and also find that there's 3 modes, shown here on the rug plot. And so these are ways in which we can just gain some sense as to whether the models are sensible. And the same over here, right? So there's like all these interesting univariate and also earlier bivariate relationships that the models are able to re-express. Yeah, I won't go through the whole notebook, but it's linked to and it's online. Now, other things we can do are find anomalies, find outliers. So this query over here is that we want to find all of the satellites in the data table, all of the satellites in the data table which are anomalous have an anomalous value for the period. And so here we're sort of saying, hey database, estimate, find me all the satellites where the probability of the period is higher than the probability of the period conditioned on other variables that dictate the period. And so what the system returns is a collection of 5 satellites where it's sort of very likely that there are anomalies. And if we look over here, for example, you have some satellite which is 36,000 kilometers away from Earth, but it's claiming to orbit the Earth in 23 minutes, which is obviously impossible. You can't orbit the Earth in 23 minutes if you're 36,000 kilometers away. But in fact, this is a units error. So the database is sort of suggesting to the user, that's wrong, but it's actually 23 hours. So the database has sort of detected that there's something very anomalous about this value. Here, for example, it says 14.36. Obviously, 14.36 minutes is also ridiculous, but that's a decimal place error. So our database is roughly pointing to cells that have unlikely features and it's telling the user, go check these cells because they're very unlikely conditioned on the other data. Now, marginally, they could be likely, right? So it's very important that our models are multivariate. You could have a satellite which has a period of 14 minutes if it's like 100 meters away from Earth or something. Well, maybe not 14 minutes, but 14 hours certainly would be possible. Okay. The final thing we'll do is we're going to compare sort of simulations from our model to selections from the data. So here what we're doing in the top plot, we're selecting the period of the satellite, how long it takes to orbit Earth, with the perigee, which is how far from Earth it is. And what we see here are for satellites with different different categories. There's ones in geosynchronous orbit, low Earth orbit. They have these particular patterns, but our simulations are noisy. I mean, they roughly follow the patterns in the data, but not exactly, right? You can see we're significantly underfitting. We have a cloud of yellow points, whereby the true model is sort of this much more deterministic. And in fact, the reason is that these three variables, apogee, perigee, and period, are dictated by Kepler's law. But obviously, mixture models can never recover Kepler's laws. But what we can do as domain experts is override the custom models, is override the models we've learned with physical laws and incorporate those into the database. And so the way that looks is sort of, we have a simple outlier model. So we have Kepler's law over here. And then we're just specifying some satellites have probabilities of being inliers or outliers. So this is like the statistical description. And we're going to write a little probabilistic program, which we don't have time to get into in detail, but which encodes the conditional distribution based on Kepler's noisy laws. And we're going to use this to improve the simulations from our model, accounting for inliers and outliers. And so what here we're showing are, the observed data, the original data in the database, the simulations from the empirical model and the simulations from the Kepler model. And we can see that by overriding the default model with a physical model, we get much more representative samples, which are more physically sensible than just empirical models. So this is an example of improving how we can use custom knowledge to improve the quality of our models. Other things we can do, which is like clustering them, so we can, we saw that there are satellites where there's, very anomalous values, so we can ask our system sort of to classify each satellite by the error, how far its observed period is from the physically ideal period, and sort of we can say that there's a bunch of satellites which are almost accurate, almost perfectly obeying the physical laws, and then there are some which are massively wrong in the database. There are some which are noticeable error, etc. And we can sort of just plot. Here in the shaded region are like theoretically physical orbits, and the anomalies that our model has detected lie outside of the shaded region because they're not physically feasible at all. And so here we're sort of combining automatic modeling with custom modeling to try and cluster satellites and detect anomalies and find regimes in which the variation is small, noticeable, medium, and large. Okay, so that's it for the talk today. So briefly, things that we're looking to do in the future are, how can we automatically check the qualities of our models? Very important question. Can we automatically find which parts overfit, which parts underfit? Other things we're trying to do are to make even higher level query languages. Like maybe some particular person wants to know, I have a database, which missing cells should I pay to find the value of? It's like data acquisition. Or probabilistic search, finding all records that are similar to a specific record. So these are just sort of ways in which a generative model over database can be used to answer lots of different data science questions and exposing those in simple ways. And thirdly, which again we won't talk about in the talk, are sort of what are the theoretical foundations of sampling? And how can we make sure that our probabilistic programming formulation is still mathematically rigorous and sort of is semantically well-founded? So that's all I have for today, but I'm happy to take questions from the audience at any point. Yes?
My understanding of the first part, since different kernels give you different patterns, so in order to generate a very complicated pattern, you take a combination of these kernels. So first is how you decide this basic set of kernels.
Right.
Yeah.
So the question is, you have these Gaussian processes, how do you decide what are the basic kernels that you want to use, which are basically shown here. These are basically, these are the kernels. There's actually not many more kernels than the ones shown over here. There's compositions, which get more and more complicated ones. But mostly in the literature, there's only a few basic patterns that people use. And so you could remove these, like maybe there's no periodicity in your data, you'd remove the periodic kernel. So you might, or reduce its probability. But yeah, there's really a small set of commonly used kernels in the machine learning literature.
And sometimes you use sometimes you use product.
Mm-hmm.
How do you decide which one you use?
Right, so the algorithm is sort of trying to determine whether sums and products give you a better fit. So you can think of, here for example, data like this. You need a product, if you have a periodic function whose amplitude is increasing, over time you need a product of linearity and periodicity. If, on the other hand, the amplitude is fixed over time, it's going to be a sum. So what the inference does is it checks the product, checks the sum, and then determines which one is actually fitting the data more accurately. If there's an increasing amplitude, then it's probably a product. If the amplitude is fixed, then it's probably a sum.
So the algorithm will do this for you, right?
Yes, absolutely. The algorithm is, I probably went a little bit fast, but the algorithm is using these kind of moves on the computation tree to try and detect whether you want to change kernels, you want to change sums into products, et cetera, using MCMC sampling.
And I think for the kernel, you also have parameters, right?
Correct. They're over here.
So you also,
yeah.
so that's the parameter within the kernel.
Correct.
Okay.
Correct. These are the parameters which we can tune, like using sampling or using differentiation or gradient optimization. Yeah. Yes.
I have a question about this slide, actually.
Sure.
So you mentioned that you're sampling from a PCFG to get the initial tree structure for the program. And then you're also running this MH algorithm to decide when to split nodes into more primitive operations.
Correct.
Are those two steps not redundant, or could you have rolled that into one step where you would start with a single node and then run an MH on that repeatedly?
Yeah, that's a very good question. So the question is sort of, do you initialize using a PCFG or using some deterministic process? It actually turns out that in order to prove your algorithm converges, you need to sample a program. You need to make sure that your prior, the only condition you need is to make sure your prior has full coverage. So if you start with a single node, that doesn't give you full coverage over the space in the prior. It's a deterministic thing. So there you run into some theoretical issues with convergence.
Okay, I assume that has to do with the particulars of MH. I'm not familiar with
Correct. MH in particular over tree structures like this.
Okay.
Yeah.
I have a follow-up. So do you have an idea of how much MH modifies the tree structure?
How much in terms of runtime?
No, how much in terms of it changes from the original tree that was sampled?
Oh, significantly. So the initial guess is going to be probably garbage.
Okay.
And you're going to iteratively, these MCMC algorithms iteratively improve the quality of the model over time. So it can be quite significant. And our prototype implementation runs in can take seconds to minutes to hours, but developing high performance implementations of these I don't think is a significant research risk. I think there's actually just engineering work that needs to be done to get results like this in minutes. Using better performing systems than Venture, which is the system we use to implement this. Yes?
I also have a question about this slide.
Yes.
I was wondering, when you're sampling the new program and trying to decide whether to accept that one,
yep.
Do you have to run the new program on every data point in your data?
Very good. So, no. There are ways to incrementalize the computation. So, for example, here, if you want to rebuild the new covariance structure, the new covariance kernel, there's no need to recurse down this part of the subtree because you've already, if you cache the intermediate results at all the nodes, when I repropose, I only need to visit this node. I never need to go recompute I never need to go revisit data and compute the covariance under this part of the node, under this part of the subtree. So there's some caching tricks you can use to reduce it. Yeah. Now it turns out in Gaussian processes, the fundamental operation is matrix inversion, which is O of n cubed. That's sort of just a Gaussian process thing. And yeah, in that case, you do need an n cubed operation at each step. But there are various sparse approximations that people use to reduce that to n squared, or even linear approximations. But it's a very good question, especially for this domain, because you have the n cubed Gaussian covariance kernel, which you need to invert. But yeah, for this tree, you don't need to rerun the tree each time. You can cache the results.
So in sampling through these different Gaussian processes, you make the assumption that training for each of the kernels, it's a straightforward process. And those who have worked with GPs, they know that training is extremely unstable. So if you can comment on that. And secondly, I was curious, okay, Gaussian processes have sort of a very nice structure, very few things to play with, still very complicated. How about extending all of these ideas to neural networks where the architecture and many other things are coming to play a role? Is there any progress in that direction?
Yes. Good. So the first question is about the stability of learning Gaussian processes. Are you referring to the numerical stability or the statistical stability? Yeah. The numerical stability, yes. So our system is sort of not as clean, the backend system, the Gaussian process library is not as clean as what I showed in the slides. There are multiple points where you need to catch things like numerical overflows, etc. The way we try and get around that is by adding white noise and increasing the probability of white noise, which can improve the stability when you're trying to invert these matrices. Like in the limiting case, you just multiply by a ton of noise, which is going to make it a very easy problem. So we sort of try and use Gaussian noise to get maybe less quality fit, lower quality fits, but make the learning a little bit more stable. And that's why white noise is an important kernel. The second question for neural nets. So there is work, I think, in trying to learn the structure of neural nets. Part of the reason I guess we focus on GPs is interpretability. It's like we want to be able to interpret what our models are learning. And I think the second reason is that the topology of the Gaussian process covariance is much simpler than a neural network which is deep, where you can have number of nodes per layer, the number of layers, the weights per layer. So I think there, like the structure learning problem is much more complicated. And to the best of my knowledge, like I know some people at Microsoft Research have been trying to do structure learning over neural nets, is that field isn't really progressing in the way that they expected because of the challenges of sort of, the depth and the width of the trees and all the hyperparameters. Whereby here we have binary trees, so we can sort of try and simplify or have simpler structure to search over. Yeah.
So, with right now the way you present it is just kind of like, it seems just general like vanilla GPs. So in like more the context of kind of more current GP methods of using inducing points, convolutional kernels, KISS GPs, stuff like that. How exactly would those additional hyperparameters fall into your decision tree, and how would you see that in like your computational load?
Right. So I think the most direct thing you mentioned was inducing points. Those are used for sparsity to reduce the O of n cubed cost. So inducing points, you try and find, instead of using all the data, a subset of the data around which you're going to induce